So people ask me all the time, am I a pessimist about climate change or am I an optimist about climate change? And the answer to that question is yes, I am both. I'm very pessimistic about the situation that we find ourselves in because I think it's a lot more serious than most people realize. And as we're going to talk about with our guest today, the reason for that is how greenhouse gases work. Basically, what happens is when you emit them, their full effect doesn't become readily apparent until a little while after that emission has happened. And so our behavior hasn't really adjusted to the reality of what it is that we've done. We don't really realize that the greenhouse gases that we've already emitted are going to mess the earth up in a pretty serious way. We're about to find that out, though. So that factor will change shortly enough. And indeed, that's precisely the reason that I'm optimistic, because humans, when our minds are focused on a problem, when we are scared by something, we tend to innovate. And not just that, it's people in their 20s and 30s and 40s that are traditionally the source of innovation. And I think that combination of people generally being quite worried about this, having more and more reason to be scared about it because they can see over the next 5 to 10 years what the actual physical effects of this thing are, plus the fact that most of the people that are going to be most concerned about it are people that are also from the generations that tend to be most innovative. I think that combination of things is likely to result in a significant amount of solutions. And indeed, many of the people that we're going to have on this series are already proposing those kinds of solutions or have already invented those kinds of solutions. So the process of figuring out whether I'm right about this, which is what the purpose of the show is. In other words, the purpose of the show is to try to go, okay, maybe Munden, you have this opinion about things because you have a particular view. Your job is to try to figure out climate solutions. And maybe you're thinking this way because you can't possibly admit that there's no way that we are actually going to tackle this problem because psychologically that's just too difficult for you to do. Fair enough. That may be. Indeed, I'm kind of curious about whether that's the case myself. So starting today, we're going to figure this out by looking first the problem in the eyes with two excellent climate scientists who are going to take us through in some detail the situation that we find ourselves in. And that examination, which is the most important thing that we're going to do on this show because it sets the basis for everything else that we do, that examination is absolutely essential because we can't tackle problems, we can't solve problems, we can't figure out how we're going to do all this if we don't have a full appreciation of exactly what the character is of the mess that we find ourselves in. And it is a mess. So I hope you'll find the episode informative, and I thank everybody for joining us.
I'm not a scientist.
Well, listen, I'm not qualified to debate the science over climate change.
Let the scientists decide that.
I'm not a scientist. All I can tell you is
I don't know the science behind climate change.
I'm not a scientist.
This is I'm Not a Scientist by TMP Climate.
All right, so last August, some scientists at the Woodwell Climate Research Center published this really extraordinarily simple yet quite important report. And they used essentially basic arithmetic and demonstrated that this scenario, which they call RCP 8.5, and that's a scenario that a lot of climate scientists have been calling like alarmist or highly unlikely, that this scenario is actually the closest match that we have for what's happening in our atmosphere. So, not great news. Their findings don't just challenge what we think we know about climate change and how it's going to play out in the 2020s and 2030s. It also has an impact on what kind of solutions we may have available to us to make our planet livable. And so that makes the challenge, both more urgent and more difficult. And we've got a couple of folks from Woodwell on the show with us today to talk about not just that report, but also some of the implications for what we call climate risk a little bit more broadly. So joining us are Dr. Christopher Schwalm and Dr. Alex Nagley from the Woodwell Climate Research Center. So thanks for coming on.
Thank you for having me.
Can we talk first about greenhouse gas emissions? And one of the things, as the title of the show goes, I am not a scientist. So I came into this profession. I do work on climate change and climate related issues quite a lot. But I came into it from a non scientific background. And one of the things that really surprised me at first was in learning about the particular impacts of greenhouse gas emissions, that they're delayed essentially. So it's not an instantaneous effect. You emit a certain amount of greenhouse gases now, and you kind of got to pay this price over a period of time into the future. Can you talk just a little bit about that and explain exactly how that dynamic works?
Yeah, sure. I can go ahead and take a stab at that. So, really, the idea behind greenhouse gases, and to me, I think it makes a lot of sense to focus just on carbon dioxide, CO2. That's really the elephant in the room. And I guess what I mean by that is, if you think about climate warming in general, CO2 alone, that single molecule, is probably about 75% of the overall problem, right? So the lion's share of what we call climate change is related to a single molecule. So I think it makes a lot of sense to focus on that. And in terms of this lingering, the idea here, simply put, is that once a molecule of CO2 is injected in the atmosphere, it stays there for quite some time, on the order of hundreds of years. So that's this whole idea of lingering, or lag, if you like, right? That if I go out and cut down a tree, and because of that, some CO2 enters the atmosphere, that will have a impact. It is atmospherically active, quote unquote, for decades upon decades, if not centuries. And that's a big, big reason why, just to link back to what you said, we have to pay that price over time.
So I just want to be clear on that effect, because it's not, as I understand it, repeating again that I'm not a scientist, but as I understand it, it's not a uniform effect over time. In other words, it's not that you're paying the exact same, say for 100 years, you're not paying the exact same price every year. It varies based on how long after the event it is. Is that accurate as well?
Well, it depends on the type of event and the type of consequences. One thing you have to, I mean, one, I think, useful frame here is this idea of a bathtub, right? And so if the spigot's open and the water coming out of the bathtub, we can, kind of sort of think of as CO2, then it becomes very difficult to effectively say, well, this one molecule of CO2 caused this one thing, right? Because it's this continuous stream. And the way to think about how CO2 influences climate is it's really the cumulative amount of CO2 that's ever been injected into the atmosphere since the dawn of industrialization.
So basically what you're saying is that we kind of pay this overall cumulative effect over time. And so when I think about the bathtub analogy, I'm thinking, okay, you're talking basically about a bathtub without a drain. In other words, we're only really working to fill up the bathtub over a period of time. There's no sort of natural process by which these emissions are eventually reduced or escaped from the atmosphere or something like that. Is that accurate?
No, there is indeed a drain, right? And the issue, just to stick with the bathtub and to stick with the bathtub analogy, is that the amount of water coming into the bathtub is significantly greater than the amount of water leaving the bathtub, right? So level is rising. And that also links back into this kind of lingering idea that you had articulated earlier.
And you talk about CO2, but I just want to clarify for the audience, because sometimes this comes out in the press, that there's another greenhouse gas that you hear a lot about, which is methane. And so some of the things that you read about methane are, well, it's a lot more serious. It causes a lot worse climate impacts, that sort of stuff. But what you're saying is essentially the issues that we have with climate change more or less boil down to CO2. Did I get that right, or is that inaccurate in some way?
I feel that's a very accurate statement. It's the largest puzzle piece in the box. Again, on the order of 75% of the problem can be traced to CO2.
So on a per molecule basis, methane does have a stronger impact, but because there's like orders of magnitude more carbon dioxide in the atmosphere, as Christopher said, that's where we're seeing the strongest impacts from.
Now, Alex, you're a specialist in something called physical climate risk. And that's going to be very important for the discussion that we're going to have today. So I just want to start with a quick definition of exactly what that means, physical climate risk.
So Christopher and I are both in the physical climate risk group. And what that means is that we're studying the impacts of climate change on people, on the economy, and on national security. So that could be sea level rise, heat index changing, any number of factors.
last sort of formative question before we get into the details of the report that you authored, Chris. A lot of that report relies on something called a representative concentration pathway, which I'm basically sure that nobody's going to know what it means. So if you could just briefly explain that so we can understand what the hell you're talking about thereafter, that would be helpful.
Yeah, right. So what that is a scenario. And that's a very important word because it's not a forecast. It is a projection of how future climate will evolve, giving a set of assumptions, which are oftentimes in this space called stylized facts. Again, to really drive home the point that we're not trying to divine the future. We're trying to understand what a particular plausible scenario might be. And where these scenarios come from ultimately is something called the Kaya identity, which is a very straightforward mathematical expression. And simply put, it has emissions being a function of three things, which is population growth, economic activity, and technological innovation. And these can be disaggregated even more. If you want to think about population growth, it really is just the number of people. If we want to think about economic activity, that is oftentimes, in terms of the Kaya identity, we oftentimes use GDP per capita. And in terms of technological innovation, there tend to be two different terms that one can use. One is this notion of the energy intensity of GDP, right? So that is, how much energy does it take to generate a unit of wealth? And the final one is this idea of a carbon footprint of that same energy, meaning that what is the price in CO2 per unit of energy, right? And so based on those things, we can come up with a fairly high level picture as what type of levers we have, right? I mean, fundamentally, what that means is there's some notion of population control would obviously decrease the amount of emissions, right? This notion of you hold everything equal, and obviously the more people you have, the more stuff you need, and the more stuff you need, there's more CO2.
So basically, what an RCP produces is, and the reason that it's called a representative concentration pathway is that based on this kind of set of Kaya assumptions, how many people we got, how much money we got, how much technology we've invented, we say, okay, based on that representation of the world, we think that there will be certain concentrations or amounts of greenhouse gases in the atmosphere on that basis, right? Okay. And to get into the paper that you wrote, which I found really fascinating, it was it was 2 pages long, but it was really clearly presented. Y'all had a look at something particular called RCP 8.5, which I'd like to first understand what that exactly represents. People sometimes call it the business as usual scenario, but if we can get into a little bit of specifics of what RCP 8.5 represents and why it's so important.
Right. So yeah, RCP 8.5 is oftentimes referred to as the business as usual scenario. What it is it really talks about human history moving forward with a fossil fuel intensive pathway. Right. That is its fundamental premise. And it was articulated really in the beginning of the 2000s. And one way to think about this is it's a very much an expert driven exercise where individuals are trying to effectively divine the future, right? And we're obviously really concerned with the level of CO2 in the atmosphere, as we've talked about earlier. And so you have to imagine several potential pathways for us to move forward. And by pathway, I mean a certain level of emissions. And in terms of the RCP 8.5, the idea here was to take one that's on the extreme high end of all potential pathways, right? And that's precisely what RCP 8.5 is. Again, it's just this very aggressive take on fossil fuel use.
Now, one of the important things I want to make sure that we understand here is that RCP 8.5 starts at a certain point in time. In other words, that's an assumption starting what year?
Yeah. So in terms of the scenarios, it starts in 2006.
So as a result of that, and this is kind of crucial to understanding your paper, because it's now 2021, we have a little bit of experience to understand whether things since 2006 forward match a certain RCP scenario.
Yes, precisely. Yeah.
And so what did you find about because as I understand the paper, you compared the various RCPs. What were your findings? What did you discover about the behavior that we've had over the last 15 years?
Sure. So since the since all RCPs were articulated in the early part of the century, and now we're in 2021, what that means is we can look back in time where we have the scenario value, right? In other words, the amount of CO2 emissions that is attached to RCP 8.5, right? And then, of course, we can look at what actually happened. We have fairly good data on this, right? And that means then that we can, in effect, compare one with the other. Okay? Very straightforward idea. So going all the way back to 2005, I think I said 2006 earlier. I apologize for that. So we go all the way back to 2005, and we simply look at what the RCP scenario said and what actually happened. Okay? And we do that for all possible RCPs. There happen to be 4 of them. And when you do that, you find that RCP 8.5 is actually the closest match. It is within 1% of what happened historically.
I see. All right. Well, let me try to square that with what I read. And, again, not a scientist, but fairly big consumer of information about climate change that you see in the media. Very often, when you see RCP 8.5 discussed in the more climate-related media, it's portrayed as an extreme scenario, kind of an outlier scenario, something that we shouldn't think very much about. And yet, y'all's results say it is the closest possible match for our behavior over the last 15 years. So how does that square?
Right. So not only is it the closest possible match, it actually underestimates the amount of carbon dioxide that we have emitted into the atmosphere. Right. So this idea that RCP 8.5 is overly pessimistic or alarmist is just simply put something we're not seeing when we look over this period, right, between 2005 and 2020. For all intents and purposes, we are on RCP 8.5. So we are on this very aggressive scenario with regards to fossil fuel use. But I mean, truth be told, that really shouldn't surprise. I mean, if we think back to the economic recovery that occurred after World War II, humanity has been on a very aggressive track with regards to fossil fuel use, and we're simply continuing that moving forward in time.
But one of the things I was also interested in when I read the paper is that it's not simply fossil fuel use that's causing some of these emissions. There does appear to be something of a role for what they call land use, which I'd appreciate if you could explain, and then explain a little bit the impact and proportion of that impact.
Right, sure. So the vast majority of CO2 emissions are related to the use of fossil fuels. So you can think in the transportation sector, you can think in industrial uses, for example, the making of cement. But that's only one kind of broad pathway, right? This idea of combustion in a more industrial setting. And that's responsible for about 85% of all emissions, if we think back over the past few decades here. The other 15% is very much related to something called land use, land cover change, which is somewhat of a mouthful. The best way to think about that is deforestation, right? It's the cutting down of trees and doing something else with that land. And probably a very good example of that is to think about what occurs in the Amazon basin, where a forest, a tropical rainforest, is clear cut, oftentimes with some form of slash and burn techniques. And instead of growing trees, you're growing soybeans or cattle. And this change from a forest to a non-forested system actually incurs a cost in terms of CO2, particularly if the clearing is done using fire, because fire very much emits CO2 into the atmosphere. So this form of land use, land cover change is probably best to think about it as deforestation. It is responsible for about 15% of the total level of emissions in any one given year.
Another thing that you asserted in the paper that I thought was interesting is that RCP 8.5 isn't just kind of the closest match to what we have up over the last 15 years, but it's also potentially quite useful going forward. Can you explain to me why y'all thought that?
Yeah, right. And by going forward, we're really only looking out to 2030 or 2050, right? we didn't want to go too forward because we wanted that time horizon to be aligned with kind of the climate policy window you might think about in the context of the Paris Accord, and also some broad notion of large scale capital expenditures, and also some notion of 30 years because that's conveniently how long most mortgages are when you buy a home, meaning that if you go out and buy a home today with a 30-year mortgage, you're effectively already dealing with the anticipated climate in 2051. So we didn't want to go to the end of the century. We really wanted our analysis to be much more actionable from a policy perspective. So we go out to 2030 and 2050. And a good way to do that is to simply look at reasonable forecasts of the demand with regards to coal, oil, gas, and so on. And you can, of course, get these from the IEA. And you then construct these pathways where we take land use, land cover, again, the deforestation piece. We simply take that trend and move it forward in time. And you combine that with the emissions forecasts that come from IEA. And you compare those with the 4 RCPs yet again. And what you find at 2030 as well as 2050 at RCP 8.5, again, the business as usual, this aggressive scenario is still very much the one that matches anticipated trends the closest.
Now, this starts to get to the point where you get in a little bit more to my end of the business, which is how an understanding of what's physically likely to happen with climate change translates in to how politics work, how our societies work, how our economies work. And one of the overwhelming truths that I believe is increasingly self-evident is that there's this kind of middle period here. So when you talk about focusing into a time frame that people care about within, say, a period of a 30-year mortgage, I'll go even tighter still. And I will assert that we need to understand what's going to happen from 2025 to roughly 2035, because if the physical climate impacts, the risks, are significant enough, we're going to find it very hard to cooperate with each other. And so the emissions reductions that we will need to make in order to have a viable planet are not going to be possible because we're going to be too busy bickering with each other as a result of this very near-term climate change. So focused on that specific topic, I'd like to move to Alex and talk a little bit about some of the physical impacts we can expect to see just from the climate change that we've created with our emissions over the last several decades and the emissions that we're likely to produce over the next 5 to 10 years. Can we first start off with just a brief discussion of some of the basic things that we would expect to change?
I mean, so to start, one of the first things we see is that the global average temperature is warming. And so that doesn't mean that every single place on the planet is warming the same, but as a whole, the planet is warming. So we're seeing warming in more places than we're not. And then that's also tied to changes in precipitation. So rainfall, we're seeing more extreme rainfall events. And then we can think about sea level change. We're seeing the melting of ice caps and ice sheets in the Arctic. And that's a really big issue. We're seeing sea level rise globally. And those are just some of the first ones that we're thinking of right now.
So those are two slightly different categories in my experience of climate impacts, in the sense that temperature and precipitation, especially in some of the countries that I've worked in developing countries. So here we're talking, Central Africa, Latin America, Southeast Asia, a lot of rural communities, especially. And to be clear, we're talking about hundreds and hundreds of millions of people living in these places, feel that impact pretty quickly. So when you're talking about a change in the average temperature, in a certain way, the average is not the actual, right? So you see a change that doesn't sound like a whole hell of a lot, a couple of degrees Fahrenheit, or maybe 1 degree Celsius, or something along those lines changing. That doesn't, okay, so it's slightly hotter. Fine, no big deal. No, that's not what actually happens if I understand it correctly. And certainly not what the people that when we go to these places and we work in these places tell us is happening, which is that they're seeing a lot spikier temperatures. So a lot more days of more extreme heat, Similarly with precipitation, that they're seeing a lot more days of extreme precipitation, either because it's not raining at all or because it's raining far too much. Those impacts, I don't know if climate science has a good way of talking about those impacts, which are physical, as different from the sea level rises, which are a little bit more kind of gradual in their effect. And the reason that this distinction, at least in our work, seems to make a difference is because changes in temperature and changes in precipitation tend to lead to a lot more disturbances of people's lives in the immediate term, and so cause problems socially, politically, economically that are a lot more immediately visible to us. Whereas the sea level rise is kind of a slower, more gradual effect. I mean, first off, is my understanding based on the work that we do accurate, or maybe I'm wrong about that? And second, is there a good sort of vocabulary in climate science to talk about these kind of risks that are a little more apparent immediately, and the ones that are a little bit more apparent in the long term?
So I think one way we can think about it is these looking at the time horizon. So there's these more these impacts that will manifest more in the near term, and then these gradual change, which they seem less obvious even though they're still happening. And I'd say that for people in Florida or low-lying island nations, that sea level rise is very much a concern for them, even though for a lot of people who are in the middle of the country, that's not something that's really on their radar. And then I think you made a really great point about a lot of countries or communities in developing countries that are dealing with these extreme events. Before I worked here, that's something that I did myself. I was in Morocco working with communities that were trying to build resilience to these changes to climate change. And they were facing both extended periods of extreme drought and then more intense precipitation events, which was leading to landslides and destroying their crops, their infrastructure. And so for a lot of communities, they're so dependent on their environment. Whereas, in Japan and Germany and the United States, so much of what we experience, we're so far removed from the agricultural system or maybe the direct impacts of sea level rise. So it seems less evident to us, but a lot of people are experiencing these impacts firsthand.
So also when we're talking about physical climate risks, it seems to me that one of the important things for folks out there to understand is that although we're seeing average temperature changes in a certain way over a period of time, that's not really uniform for the entire world. In other words, certain parts of the world are seeing much more significant temperature changes than other parts of the world. And I wonder, Chris, if you could discuss that a little bit and what its implications are.
Yeah, sure. So I really think it can be summarized in a very simple idea, which is the poorer you are, the hotter it gets. That's something that's very much going to characterize how climate impacts are distributed globally, is that nations that simply lack the political infrastructure, the economic infrastructure to deal with climate impacts are going to be those same nations that are going to disproportionately suffer the most.
And that's just sort of random bad luck physically. In other words, they just happen to be in the wrong places on the planet where this is more likely to happen, and sort of through no fault of their own. They're both not the people that caused the problem in the first place, because the emissions come basically from our countries, but also happen to be in the places where they're going to get hit hardest first.
Yes, yeah, that is exactly what's going to happen. The kind of bulk of emissions historically are not really associated with countries that are close to the equator, right? If you look at a map of where developed nations are located, they are located in more temperate climates, typically speaking. But again, the impacts of climate change will come home to roost in a much more violent manner in those nations that are closest to the equator, as opposed to the temperate climates of, let's say, a Japan, a United States, a Germany, and so on.
Now, when we talk about this coming home to roost in a more violent manner, what sort of time frames are we talking about here? I think it's a little bit abstract for everybody in a certain sense when we talk about this stuff, because when we talk about climate impacts, it's not so clear exactly the sort of things specifically that you would expect to change, right? You expect temperature to change. You expect precipitation to change. Um, I mean, we're going to see more like cyclones and hurricanes and that sort of stuff. What exactly are these violent sort of climate impacts that people are worried about? And especially, when are we going to start to see those sorts of things happen?
Yeah. So I really think that the best characterization is a world of more extreme extremes. So any type of climate and weather extreme that you can think of will simply continue to get worse as we move forward in time. And in terms of when are we going to start seeing those, we already are starting to see those. If you think back through a catalog of events that have driven the news cycle over the past 2, 3, 5, 10 years, a lot of things that have emerged that have been trending are very much related to climate extremes, or rather extreme events that have a climate change component. Think about, for example, the fires that occurred in 2019 and 2020 in Australia, which the Australians call Black Summer. It's a very clear climate change component to that. Think about some heat waves that have occurred in Europe, right? Russia, France, Germany, and so on. There have been a few heat waves already during this new millennium that are incredibly rare, or rather historically they were incredibly rare, but now they are occurring at a much more greater incidence. This is going to be a emerging trend that we see with all forms of climate extreme.
Also, to be clear about a specific point, we could, I mean, obviously we're not going to do this, but we could tomorrow all of a sudden just stop emitting greenhouse gases, right? If we were to theoretically do something like that, we would have already baked in a certain amount of climate change. So, although that would be a good thing for climate going forward, we're going to have to figure out some way to navigate these near term climate impacts because we already caused the problem.
Yes, that's very much accurate. I mean, we fundamentally have three choices. We can adapt, we can mitigate, and we can suffer. And what we ultimately do is going to be a mishmash of all three.
So, when we talk about those specific three things, adaptation, mitigation, suffering, well, maybe we should just talk about the first two. Uh, Adaptation is a term that's used a lot in climate change circles, and mitigation is also a term that's used a lot in climate change circles. But my experience is that most people that don't follow climate change don't exactly understand what those two options are. So you can talk a little bit about what each of them means.
So they have very specific, very technical definitions in terms of the climate science community. Adaptation means that there are certain impacts of climate change that are effectively baked in, and we have to learn to deal with them. Again, it very much focuses on the adapt part. Mitigation means that we take measures to actually reduce the impacts of climate change. And the best way to think about that is to reduce emissions and ultimately get to something called negative emissions, which is where we effectively suck CO2 out of the atmosphere, where we actually reduce the amount of CO2 and try to push the clock back in time, as it were.
All right. So, Alex, I want to focus on the communities that you worked with in Morocco. Um, uh, these are obviously developing country communities, and so therefore somewhat challenged in terms of the resources that they've got. And also, if you think about it in terms of the challenges that they face, adaptation, mitigation, and suffering. Uh, on the mitigation front, they're not really a significant source of emissions, so they don't have very much to do there. Um, they'd obviously prefer not to suffer. So, what are the adaptation options that communities like that have? I mean, is it even possible for them to adapt to these physical risks of climate change that we're creating?
So there are a lot of different adaptation measures that communities can take. And in the world of adaptation, there's this concept of either displacement or replacement. And displacement means that you keep doing what you're doing, but because your environment is changing, you're going to have to move somewhere else to do that. And then the concept of replacement is, so you want to stay where you are, but you're going to have to make some changes to adapt to this changing environment. So in the communities I worked with, maybe they're changing some of the crops they're planting. So they're still very much agriculture based, but more drought resistant, or changing to the type of temperature and precipitation patterns they're seeing. Or possibly they're, and in other places that might be, that their adaptation might be even more extreme. So replacement would be changing livelihoods altogether.
one of the common themes for all of those solutions that you've described is money. And my general sense is that so far, rich countries, who are objectively the source of the problem that a lot of developing countries are facing, have not ponied up enough money for these sorts of things to be implemented. So when you talk about implementing, say, a drip irrigation system, even in a micro level, that costs money. That requires expertise. People that are technical experts have to come in and help them install the system, all of that sort of stuff. When you talk about things like building a seawall, that's some serious money. And yet there's been a generalized reluctance, as I understand it, for these sorts of things to be funded. So just to be perfectly clear on this point, is it possible for these communities to engage in any significant adaptation if they don't get that capital, if they don't get that technical expertise to help them?
That's a great question, and a lot of times it does come down to funding. So these projects that I worked on were in partnership with the United Nations Development Program that were funding these activities. For example, as you mentioned, drip irrigation is not cheap to install, but there are things that communities can do that I guess are less intensive in terms of the funding it requires. And these are partnerships that usually take a long time to develop.
Last question that we want to talk about today is a fairly important one because I think it's a fairly likely scenario. So, Chris, throwing this to you, and I know this is a difficult thing to talk about, but let's get real here. It does not sound like we are on a very good track with respect to reducing our emissions in the near term. And so we are continuing to sort of dig the hole deeper and deeper, in part because of this delay effect where we, the source of the emissions, don't really see or feel these major impacts of climate change that we've already kind of baked in. We're about to see them, but we haven't seen them yet. So if we don't act over the next few years to reduce emissions quickly, it would seem to me that we're inevitably going to need some more radical solutions. In other words, it's not going to be enough to build the windmills and the Teslas and all that sort of stuff. We're going to have to pursue something that's a little bit deeper. Do such solutions potentially exist? And if so, what do they look like?
I think such solutions do indeed exist. And to kind of come to terms with them, we probably have to go back to our controlled vocabulary of suffering, adaptation, and mitigation and add a fourth member, which would be geoengineering. In terms of a way that, again, it very much be a radical, if not revolutionary way to tackle this problem, I would strongly suspect moving forward that we need to spend more resources understanding the various geoengineering options that we have. There's somewhat of a taboo in working in this space, but I simply feel that our backs are against the wall. Another thing, and you're starting to see this come out there, even some.
Just to pause there, Chris, for just a second to make sure the audience understands. When you talk about geoengineering, can you just give some sense, broadly put, as to what those potential solutions might look like and what they involve?
I'll give one example because it's based on a recent volcanic eruption, Mount Pinatubo in the Philippines, I believe, in 1991. I think I'm getting my dates right. Someone should check those, though. Dumped a lot of very fine particles in the atmosphere, basically the ash plume. And based on that, there was a cooling that was not anticipated to the tune of about 1 or 1.5 degrees Celsius. It's somewhat hard to constrain this down to the second or third decimal point. But the reason I'm mentioning this is this in some sense serves as a very simple template of how one might conceptualize what geoengineering means, because fundamentally most geoengineering ideas relate to something called solar radiation management, meaning that we want to reduce the amount of solar radiation that actually interacts with Earth's climate system. And one way to do that would be to deploy mirrors that would reflect sunlight. And it turns out that the ash plume that was injected into the atmosphere as a result of Mount Pinatubo, that these tiny particles do indeed function as very small mirrors. So the notion, one idea here, one concrete idea with regards to solar radiation management is to take these same particles that are actually produced in superabundance as part of numerous industrial processes to take this exact same type of particle that again would arise from a Mount Pinatubo like eruption and to fly them up into the high atmosphere and to simply spray them, right? To inject them into clouds, to just inject them into the high atmosphere. The idea is that they then would reflect sunlight. They would lessen the amount of energy that would reach the Earth's surface.
Straight up, we're backing ourselves into a position here where the solution to our pollution is more pollution. That's kind of the hole that we've dug ourselves in. I mean, absurd as that sounds, it is a real possibility that in order to get out of this situation, we've got to pollute more.
Yes. I mean, the idea behind the particles used is they are harmless. They wash out of the atmosphere after some point in time. That's the idea. Now, if that is the case, if that were to be a sustainable and true statement over 20, 30, 50 years of this type of solar radiation management, no one, of course, really knows. But geoengineering is that level, meaning that it's in some sense like opening up a Pandora's box. There's some basic technological understanding of how it would work, but the mid to long term consequences are very much unknown. And then, of course, there's always this issue is what if you stop doing it at some point in time? How would that effectively reset the climate system? Would you lose all of the gains in the sense of lessened warming with just someone flipping the switch? Or would it be a bit more nuanced than that? There are lots of loose ends with regards to how geoengineering would work, on what timescales it would actually remain effective, the level of maintenance one would have to engage in. That is, how much you have to inject into the atmosphere and how often, where does it actually happen? And where, I mean, in terms of the geography, what about governance issues? Is this something that the UN has to tackle? There are all these things that need to be wrestled with to really articulate a coherent scenario that uses geoengineering. And there's simply a lot of basic research that needs to be done. There's a lot of basic research that needs to be done that the community has in some sense been hesitant to engage in.
Final question I think that our listeners really want to know the answer to is, y'all live, eat, breathe, sleep climate change, the physical effects that climate change is having on our Earth. It's what you spend your entire careers looking at. So you have a really unique level of knowledge about what the consequences of that are likely to be. And have over time probably developed a real feel for what is, in the end, sort of the ultimate question. Are we going to make it through this? Is it possible for us to overcome the challenge that climate change presents?
Sure. I mean, so I think it very much depends on what that particular threshold is. If we want to think about some idea of a dangerous level of climate change, I'm very pessimistic on that. We are going to be breach these thresholds within the next 10 years easily at our current rate of emissions use. And the notion of not having to suffer, right, to link back to that controlled vocabulary we articulated earlier, the notion of suffering, adapting, and mitigating. There's going to be a fair amount of suffering. I simply see no way around that. And I think it's useful just to understand where that comes from. And one place where that comes from in my line of thinking is from the ongoing pandemic, where emissions in 2020 were about 7.5% less than in 2019. That's very much attributable to the ongoing corona pandemic. For us to not breach this level of dangerous warming, we have to have that exact level of reduction moving forward in time. In other words, 2021 has to be 7.5% less than 2020. 2022, 7.5% less of 2021, and on it goes until we no longer emit. And the idea of humanity being able to get their collective ducks in a row to achieve that goal, I'm very pessimistic on that. So there will be some level of suffering, much more so than what we're seeing today. If we think about this in longer timescales, though, I think humanity will indeed find a way to cope, to address this problem, but that the world that represents is going to be fundamentally different. We really have to wrestle with some broad notions that aren't part of this debate. The idea that certain parts of our home planet are simply not going to be habitable. We need to wrap our heads around what that means. And I think until we can do that in a very forward-looking manner, an open manner, we're going to have a very difficult time stopping this level of degradation.
And I think the only thing that I would add to that is, as we touched on in the beginning of this episode, if we look at the current trajectory that we've been on and that we'll be on for the near future, it's not looking great. But again, the next 5-10 years, that's not something that, there's a lot of room to change in the next 50 and 100 years. And so will we make it like completely unscathed? No, I mean, we're already seeing the consequences in one way or another. But there's a lot of room for ingenuity and advances in the future.
Okay, well, thank you very much for participating in this. We really appreciate it. And I think the audience has found it really very informative. Thank you both so much.
Thanks very much.
Thanks for having us.
I'm Not a Scientist is a production of TMP Climate. Our theme music is by Kyle Walker. Executive producer is Dakota Castetz Didier. Post-production manager is Andrew Narvaez. Willie Munden and Tin Garcia handle our research. And finally, special thanks to Brock Anderson, Laurent Barthélemy, Ben Bowie, Kathleen Rutherford, and Peter Riggs for their contributions and occasional guest hosting. For extra content and to submit questions and comments, find us on Twitter, or if you'd like to join the community and contribute to the show, head to our Patreon page. Thank you for listening, and from TMP Climate Headquarters in Tokyo, this is I'm Not a Scientist.